Now, to continue with the association analysis in the data mining, we will look at another technique for finding the frequent item sets from a transaction database without the candidate item set generation. As we have seen, the candidate item sets can be very large, particularly when the number of unique items is very large. And to repeat, for creating the association rules, we take a two-step approach. First, we identify all the frequent item sets which have got the minimum support, and we generate high confidence rules from those frequent item sets. And a frequent pattern mining requires us to scan the database multiple times. And the longer the pattern that we have a larger number of scans that are required. For example, if we consider a potential 100 item frequent item set, then we require 100 scans before we determine. And then while doing that, we need to do numerous comparisons, because to reach the 100 item set, we will be going through 1, 2, 3, 4, one number at a time. So there are 100 times, and each time we are generating the number of candidates, and the number of candidates will become exponentially large. So we have a bottleneck with the candidate generation and testing. So the approach we take is like this. So previously we used to generate candidate items based on the frequent item sets which are of smaller size. So we started with the size 1, size 2, so on. And at each point we considered only the frequent item sets, and we started generating the supersets, and then we checked for their support. So now instead of that, if we had a mechanism whereby, let's say we have an ABC is a frequent pattern, and identify all the transactions which are supporting ABC, that is, we have some way of accessing all the database transactions which support ABC, and then there we look for a frequent item D. If the D is not frequent item, then we know that ABCD will not be a frequent item. Then we locate it within the database a frequent item called D. Then we recognize that ABCD will be a frequent item set. So this is called as a frequent pattern growth. We construct a tree which we call as a frequent pattern tree. So how do we go about is, first we scan the database once. That is a minimum thing that is required. So we need to scan the database at least once to understand what is available in the database, and then we identify all the frequent one item set in there. And then what we do is that we are going to sort the frequent items in the order of the frequency. So that is, if we have A, B, C, if we think that C is the most frequent and A is the lowest frequent, then we represent this as a C, B, A, because C is the most frequent and A is the least frequent. And then we scan the database once more. But this time what we are going to do is to construct an FP tree which captures the entire transaction information which is available, and thereby we will not be requiring to go back to the database again to find the patterns. Now let's say we have got a transaction database that has got 5 transactions, and these 5 transactions contain the items bought. And what are all the items bought? We have numerous items, so there are possibly 15 distinct items which have been bought. Then we look at the support. We identify that the 3 is the minimum support which is required. And so we are not concerned about the items which are lower than 3. So we start finding 1 items which have got the minimum support. There we realize that there are only 6 1 items which have got the minimum support of 3. So they are the frequent items. So what we see is that in this database, only these 6 items can give us frequent item sets. So what we do is that we start pruning this database. Next time we go, that's what we're going to do. We are going to remove the items which are not frequent. So we want only FCA, BMP in this. So we do not want D. And then similarly, we do not want G. And we do not want I. So we get the record FCA, MP. And added to that, we look at the support for each one of them. When we look at the support, we realize that it is F which has got the maximum support. Support is equal to 4. Others have a lower support. So we sort this list as per the support. So thereby we have got a frequent items which are sorted as per their support in the decreasing order of the support. So now when we create a table of this kind, then we will use this table to, when we do the next time the scanning of the database, we need to scan the database twice in this case. So here we are looking at a lesser frequent items, potential frequency items, and they have been ordered in the same order as their the support, and then we start constructing the tree. What we do is that first we have got FCAMP is the transaction 100. So F, we are going to create a node for F, and what will be the support for F at this point? So what we say is that it has got a support of 1. And then we create another node for C that also got a support of 1. And then we create another node A under that will have the support of 1. And under that M again with 1, and then P again with 1. Then what we do is that we look at the next transaction. Next transaction is FCABM. So we look for already for which the nodes have been created. We start with the null node. So under that there is a node for F. So we increase the support for F, and then we make it 2, and then similarly CS becomes 2, and then A is becoming 2, and then B does not exist in the tree. So we create a new branch for this, and B has a support of 1. And then M is under B, so M is created with the support of 1. So, and we link the previous M with this M in the so that it is easy to traverse to find out the overall support for M when we require it. So then we got B, FB. So we come to F, and then there is no path, though there is a B somewhere down. So we want a presence for just FB. So we are going to create a new node for B with 1, and we increment F. So finally F is going to get its full support here. And C has been dispersed. At one place it is occurring with 3 and other at 1, because once we get this transaction CBP, we are not going to traverse the entire tree for finding out whether C exists somewhere. We are straight away going, since F is the first node we find, we need to start a new branch with C. We start with C, and then B, P, we are going to create another branch. So thereby we are creating the tree which is done with the minimal traversal, and wherever required we know that there is a node for C already existing, and so we are going to take a link from the old node to this new node so that we can traverse and find out the overall support for C. So this is the overall tree that we will create, which we call it as a frequent pattern tree. And what we do is that we create a header table which has got the list of items which are frequent by themselves, that is each one item is frequent, and we note down their frequency, and we maintain a pointer to the first node which has got this item. So in case of F this is true, and in case of C this is the first time we found C, and then we add another link from here when we are going to when we had to create a new node next time. So now how do we find out the patterns which represent the frequent? So what we do is that it is now very easy, given this tree structure with a minimal number of traversal, because the traversal will be typically the order of the number of items, the number of nodes in a particular path. So for example, we want to find in how many frequent item sets the M is likely to occur. So what we do is that we locate M we come here and then we look at these items. We traverse the tree in a reverse way. From the leaf we try to reach the root, and then we will find out that A, C, F are the items which occurred with M twice, and there is another item M, another time M occurred with B, A, C, F. So if we are looking for, so that way we can create a conditional pattern base for each one of these items just by doing the traversal of the tree. So it is likely that the tree will be resident in the memory, though the database may be very large, but we do not expect the number of items to be so large. And the number of nodes in this tree, they are larger than the number of items, but they may not be so significantly larger that that it cannot fit into the memory. So once the tree is completely resident in the memory, we can see that generating the frequent item sets from this tree, since it carries the entire information of the database here in a different structure, we will be able to very quickly generate the frequent item sets. So now if we look at item C and we look at what are all the frequent items in which it can occur, what we notice is that the F is occurring within this 3 times. So which is the representing the conditional pattern base of C, which we found out only by traversing above. So though the A is occurring with the C, that will come in a different level. So because we know that C is at a higher level than A, which is more frequent. So when we want to find out the items which have a higher frequency and occur with it, so what we are doing is we find F. Similarly for A, we find FC3. So we know that AFC is going to be a frequent item set if we have a support of 3. Similarly, when we come to B, we realize that B is occurring once with C, so we cannot have a frequent item set here. And similarly, FB is once, so we are not going to have a frequent item set there. And FCAB is occurring once. So what it means is that with B, we may not be able to get frequent item sets. So, and depending on the minimum support, we are going to get different frequent item sets. But we are able to get it in a very compact form, whereby we are going to, and many times we also want to know we want to ask the questions such as, let us say we are looking at the sales in a grocery store. Most probably the store will be interested in knowing a question like, what are the items people are likely to buy with bread? So in that case, you can see that you want to look at a conditional pattern base with a particular associated item and look at all the associations with that. And that we are getting easily from this tree. So if we look at the benefits we are getting by this frequent pattern tree, one is that it is complete. It is getting the complete pattern mining information from the database, nothing left in the database. So if whatever we want to generate, the number of patterns, the support, the combinations, everything is present in the tree. And then it is very compact. And we have removed all the infrequent items right in the first pass. And we have removed the irrelevant information. For example, a transaction may have 5 items which are considered frequent, and then there are 95 other items that they bought, but all those items had not been bought in the other transactions. We removed those because you may remember in the earlier slide, we have seen that all the transactions have been compacted to remove the items which are unlikely to produce the frequent item sets. And then we have started the storing the items in a frequency descending order. So what that means is that at the top level, we are going to get the items which are going to be shared with the more transactions. So that way the tree is likely to be of lesser size, smaller size, or more compact. And tree is never likely to be bigger than original database, though it is going to store some information such as the counts and then the links. But if you ignore that information, it is not at all going to be bigger than the original database. And we can answer several questions. So we have got a frequent list FCA BMP. So we want to find out all the patterns which contain P, and all the patterns which contain M but not P, and patterns having C but not BMP. and patterns having F. So in a way, it is helping us find out, by traversing the tree, we can find out all possible combinations that are available. So from what we can do is that, having got the complete FP tree, we will also be able to generate conditional FP tree. For example, we want to do a conditional FP tree with respect to M. So you can see that there are items which are marked in blue, they have association with M. So we need to work with only this subtree and still understand all the possible association rules that we may be able to generate where M is going to be a part. So if you look at a conditional frequent pattern tree, you are only getting FCA because B is not going to be frequent. So that way we are getting this small tree. This is representing the conditional pattern base, that is representing a frequent patterns associated with the M. And similarly we can do for all other items. For M we find this, for AM we can find this, and for CM we can find this, and similarly for CAM we can find this. So all of these are representing the frequent pattern trees that are associated with patterns that we started with. And it is also possible that sometimes we get a tree which has not branched until you come down some nodes. So in this case, you started with A1, A2, A3, and only at A3 started branching. So in this case, this subtree can be converted into a single node, and we can deal with a smaller tree, and the smaller tree is easy to visualize and easy to understand and easy to observe any interesting patterns. So when we want to mine frequent pattern with FP trees, so what we do is that we are essentially looking at a partitions, and with the help of the partitions, so whenever we are looking at a subtree that is representing a partition from the database. So thereby we are able to generate the frequent patterns. And FP growth algorithm has been successful for several reasons. It works on the principle of divide and conquer. And it is first eliminating all the infrequent items, and they are never going to be part of the tree. And it is working with a focused search of the smaller database, and we are not generating any candidate items. And so in some situations we have seen that the number of candidates can be very, very large. But in this case, we never attempted to generate candidates till we have completed the tree. Only after the tree has been completed and possibly completely resident in memory, then we started looking for frequent patterns within that. And since the FP tree is representing the complete frequent pattern information from the database, we can consider that as a compressed database itself for our purpose. And then we are scanning the database at only twice. Even if there are 100 items, we have seen in some earlier cases there can be a large item sets. But we are going to scan the database only twice, and that will give us the FP tree, and from there we will find out the items. And we do not need to worry about the pattern searches and matches.